네, 안녕하세요. 감사합니다. 저는 영어로 발표할 거고요. 질문이 있으시면 한국말로 질문하셔도 되니까 이제 질문해 주시면 감사하겠습니다. So yeah, so today's talk is all about additional information understanding. It's actually a concept that I thought about before when I was in my master's degree. It's actually a vague and it's still ill-defined concept, but I want to emphasize how important understanding additional information is to create an effective supervision for NLP tasks. So before I start, I would like to introduce myself. I'm again Reinald Kim Amplayo, and I started my master's at Yonsei University 2 years ago. I already graduated, and my first research topic was all about topic models for NLP. So that's for 1 year, and I didn't really get a lot of good results from researching topic models. So I moved to deep learning last year. So as you can see, I'm still a neural network newbie. I'm still a deep learning newbie. I started just last year. So I really appreciate comments, suggestions, and if you have a lot of questions, please ask directly. And I'm also starting my PhD at University of Edinburgh next month. So if you have any questions after the talk too, you can send me an email at either of these two email addresses. So I would like to start my talk by arguing that most NLP models are in this structure. So we have text as an input, and then we we process the text using a model, and then we train the model to produce an output. So there are other types of NLP models as well, where we accept non-text as input, and then we output texts as we output text for specific NLP tasks. But in this talk, I will only focus on this kind of model. And there are deep learning has been success recently. So there are a lot of neural-based models that are being used these days. So these are like the structure of those models. So we have again an example, an input text. We embed it into an embedding space. We encode it in some way, and then we pull it, and then we use that information to classify the text as one category. Or we can proceed to attend to important aspects, and then decode text to as an output of a generation task. So here we accept a single text as an input. So my first question is the input text enough to solve all kinds of NLP tasks? So the simple answer, and it's actually very obvious, is no. And so since I'm a deep learning newbie, I got quotes from famous researchers from NLP. So the first one is from Yejin Che. She actually delivered a lot of speeches lately in this year, including AAAI and Northwestern NLP conference. And what she wanted to argue is that we need common sense knowledge on tasks where there is weak alignment. So what are these tasks? So there are where we can have summarization where we don't have alignment between the input and output, or question answering. Min Jun Seo, who is currently working at Naver, in his Naver Tech Talk, told us that we need an external or explicit knowledge for reading comprehension tasks. I would like to extend what they argue to in a general matter, where in general we need additional information, which includes both common sense and external knowledge, which was argued by both the researchers, and not only on tasks where there is weak alignment or for reading comprehension tasks, but for all NLP tasks. So what are these additional information? We can use like a lot of additional information that we can gather from other sources, such as word knowledge, so knowledge bases, the Wikipedia, the internet. We can also use related text, such as search results from a query or translations. We can also use categorical information, such as user, who like the writer of the text, topic, and sentiment. And we can also use other modes, like multimodal learning for audio, speech, visual images, and many more. So the second question is that, is using this additional information enough? So can we like just use additional information, input it together with the input text to the model, and then generate an output that is correct? So maybe people will argue that neural nets, the current neural network architecture will learn enough inductive biases to use and learn to use only useful signals. But again, I argue that the answer is no, and that we need to understand additional information. So this should be. I am arguing right now that this should be the model or the structure that we should use when we try to use additional information. So first we have the understand module, where we try to understand the additional information before we input it to the model. So what is understanding? Again, this is a very vague concept. So in this talk, I will just mention three kinds of understanding. So by asking questions. So do these additional information contain errors? If they contain errors, we try to mitigate possible errors. If they are only useful at some cases, so we condition only on those cases. And if there are any special cases, then we consider those special cases or those special problems that might occur when we use this additional information. So these were my work when I did my master's. And I tried to use different kinds of additional information for different kinds of tasks, and use different kinds of understanding the additional information. So I will start with the NAACL paper, so where I use knowledge bases and linked entities as additional information and tried to mitigate the possible errors that might occur. And so this is the paper. It's entity common sense representation for neural abstracted summarization. And the task here is summarization. So given a long text, we try to generate a shorter version of that text, which corresponds to the summary of the long text. So we can have long sentence and then output a shorter sentence, or we can have like a very large news article and output a few sentence summary. And we use in this paper we use an abstractive summarization approach, where in this approach the sequence-to-sequence model with attention is widely used. But there are a lot of problems, as you might probably have seen in the literature. But in this paper, we tried to solve one problem, which is that it tends to put irrelevant information in the summary. So what the sequence-to-sequence model with attention does is that it encodes all the information found in the longer text and tries to decode all the information to produce the summary. But actually, in our input text, there are relevant information that might not be needed in the summary, and this is a problem since, especially if we try to summarize longer text, because there are a lot of irrelevant information that might not be needed in the summary. So one thing that we thought about is that what if we have the topic of the summary, and if we know the topic of the summary, we can control what the decoder will decode every time it generates a summary. So our idea is to use linked entities as additional information to capture this topic of the summary. So there are three kinds of observation, which is actually an advantage when using linked entities as additional information for summarization. So the first one is that summaries are actually mainly composed of entities. As you can see here, if you extract the entities from the main text, you get Los Angeles Dodgers, South Korean Jeso, New York Mets, Wednesday, and Swap. And most of them, actually all the relevant ones, are in the summary. So South Korean is Korea's, Jeso is So, then Los Angeles Dodgers is Dodgers, and actually all the nouns here that are found in the summary are linked entities. So so that's the first observation. The second observation is that we can use entities as the topic of the summary. So again, if we have this these entities at the bottom, we want to translate this into a summary topic. So we represent summary topic as the multinomial distribution over entities, which is given there. So we want to translate these entities into a probability distribution, where, for example, in this case, Jeso is more relevant than South Korean because it has a larger probability. And then lastly, we have we can use entities as common sense knowledge, where again we would know that Los Angeles Dodgers and New York Mets are baseball teams. Jeso is a South Korean pitcher from New York Mets, and so on. But there are also problems because the entity linking system is actually erroneous. So the first problem is the ambiguous entities. So in this example, we have South Korean. It may refer to the person. It may also refer to the language. It may also refer to the adjective, just the adjective South Korean. So that's the first problem. The second problem is on course entities, where there might be words that are not really entities but are linked by the entity linking system. So in this case, we have Wednesday and Swap. So Wednesday and Swap are actually just ordinary words. They are not entities, but they are linked as entities by the entity linking system, and this is a problem because it might be wrongly linked into, for example, Wednesday to Wednesday night baseball, and then Swap is not really. It's arguably correctly linked to trading in sports, but it's too common to be considered an entity and to be considered as part of the topic of the summary. So we propose entity to topic module, where there are 3 steps, and the first step is to extract link entities from the main text using entity linking system, and the second and the third step is actually the meat of this model, where we try to solve the ambiguity and the coarseness problem. So the second step is to encode the entities. So here we try to solve the ambiguity problem. So first we embed these entities into the embedding space, and then we try to disambiguate the entities using the entity encoding submodule, where it composed of disambiguating encoder and selective disambiguation mechanism. So for the disambiguating encoder, we try to use 2 kinds of encoders. We try to use RNNs, where it uses global context to disambiguate a single entity, and we also try CNN, where it uses local context. And the selective disambiguation tells us whether to disambiguate this entity or not, because not all entities need to be disambiguated. There are entities that are ambiguous, but there are also entities that are not ambiguous. So we use a sigmoidal gate signified by D, where it measures how much of the meaning should we disambiguate or not. And then for step 3, we try to create the summary topic vector, and in this step we also try to solve the coarseness problem by using the firm attention mechanism. So firm attention mechanism is a slight modification of the soft attention mechanism. In the soft attention mechanism, the soft attention, it gives importance values to all entities, even if the entities are not really relevant. So this will impose noise to when we create the topic vector. So we use firm attention. Again, this is just a slight modification where we where we pick the top k entities and we do softmax on that top k entities. And then finally, we try to use this entity to topic module to sequence with attention model by using the final output of the decoder as the document vector, as signified by the yellow box. And then we concatenate the summary topic vector with each state in the decoder, as signified by the green box. So one advantage of entity topic module is that it's easily attachable to other kinds of sequence-to-sequence models as well. So in this paper, we just use sequence-to-sequence with attention as our base model, but we can use the entity topic module to other sophisticated models as well. So the results are as follows. So the gigaword dataset is summarizing a long sentence into a shorter sentence. In this dataset, we didn't really we have a comparable results compared to the state of the art at the time of the writing of this paper, but we have we found significant improvements over the base model, which is the sequence-to-sequence plus attention. We also tried human evaluations to compare whether compare between CNN or RNN, which one is the better disaggregating encoder, and we found that CNN is the CNN variant is better than the RNN variant. And finally, we also did we also ran our model to CNN dataset, where we tried to summarize a large news article into fewer sentences. And in this case, we have very significant improvement over the base model, and we also defeat the current state of the art at the time of the writing. And the thing that we should look at here is that when we don't answer the ambiguity and the coarseness problem, if we don't use the selective disaggregation and firm attention mechanism, we won't achieve the high improvement that we achieve when we use both of them. So again, so here we try to understand the linked entities, and after understanding the linked entities, we achieve the significant improvement over the base model. So this is just a quick analysis on how selective disambiguation selects which entities to disambiguate or not. So I'm just gonna skip this, and then we move to the example. So we have an example for GigaWord and for CNN. So for CNN, you can just look at the paper. So in this case, this is the GigaWord dataset example, and as you can see, the sequence-to-sequence plus attention base model and the E2T module with soft attention, they both have Guadalajara in the summary, which makes the summary fake, because Guadalajara is not actually the state. The state is actually Jalisco, but like since the soft attention focuses also on the Guadalajara entity, it also mentions Guadalajara here, which again, it's not really relevant to include this in the summary. So again, firm attention removes the erroneous or the UNK and then the less irrelevant entities. And then selective disaggregation, here the linked entity is actually linked to US state, but since we use selective disaggregation, both soft and firm attention mention Mexico state instead of the US state. So the conclusion of this paper is that we can leverage on linked entities to improve the performance of abstractive summarization models, but we need to address ambiguity and coarseness issues. So to address those issues, we use entity topic module with two submodules, which is selective disaggregation for the ambiguity problem and firm attention for the coarseness problem. And then we show significant improvements over the base model, which is the sequence-to-sequence plus attention, on the GigaWord and CNN datasets. So yeah, so this is the first paper. So is there any questions?
Yeah. I'm sorry. So okay. So how can we define the topics for the pooling and firm attention, right? So how can we define first? How can we define the number k? for the firm attention. The second one is so you want to get some score or topic distribution for the rating some scores, right? So how can we define the dictionary or something, vocabulary, something for the topic? So in your entity to topic module and write figures, your the scores, kind of some the purple boxes, right? So how can we, what values correspond to the
box.
To the box, yeah.
Okay. So the first question was about the how do we define K? So in this paper we just tune K using a development set. So our findings is that in the gigaword dataset where the sentence is short, the K is 5, and in the Siena dataset K was 10. We used like 5, 10, 20, 50, 100, and so on. And yeah, so like we just tune the number of the top K, so the K value. But like there are actually a lot of recent works on improving soft attention to make it sparse. So there is like sparse max, fuse max. If you want to experiment on that, I think they can also. And then the second one is, yeah, we use attention. So the weight of the height of the box is actually the attention weight from the So that corresponds to so again the topic of the summary is represented as the probability distribution over the entity. So we don't so our vocabulary here is the entities.
The yellow box is the document emitting means kind of some from the encoder part, right?
Yes.
Okay, I see. And the next slide.
Next slide.
So the second row groups, what is SD?
SD is the selective disambiguation.
Okay,
so,
I see. Okay, thanks.
Okay. Any other questions? So I'll proceed to the next paper, which is using translations and understanding translations to condition only on useful cases. And this is for sentence classification. So again, the task is sentence classification. So we have a sentence as our input, and then we try to classify if it's, for example, positive or negative, if it's sentiment classification, or we try to classify what type of question it is for question type classification. So the critical problem here is that we have a very limited context because we only have a sentence to extract our features from, and again, so this is very limited. So what previous solutions did is to expand the context by using neighboring sentences. So if there is a neighboring sentence, then we can use that to as a feature extractor as a feature extractor as well, or we can use the full document. We can also use the latent topic. So we use like topic models like LDA to induce latent topics from the sentence, and then use that as an additional information. But these current solutions are actually domain dependent. What I mean by domain dependent is that they are not available on certain tasks. So for example, in search queries, if we have queries as sentences, we don't have neighboring sentences, we don't have full documents. And also it's not useful for certain domain-specific tasks. So in movie reviews, we have a limited, the topics are limited, so we don't really have a very diverse topics to be used as good additional information or additional supervision for sentence classification. So here in this paper, we suggested to use translations as domain-free additional context, and it has many advantages. So the first one is that translations are always available, especially since recently we have a lot of neural machine translations. And then we also have a lot of translation services such as Google Translate, Papago, and Baidu Translate. We can use those to translate to as many languages as we want. that's actually the second advantage, is that we can extend our context as many as the language as possible. So if you want to extend it 5 times, we can just use 5 languages, and so on. And then the third one is that we can translate. We can use the translated sentence as an ambiguity resolution system, where, for example, in this example, we have the movie is terribly amazing, and terribly is actually ambiguous and an ambiguous word. And if we translate it to Korean, it will be translated like this, which means the movie is greatly magnificent. And then last, we have this figure, where it shows that specific languages are better in classifying a specific class. So in this figure, we showed Arabic vectors and English vectors. And as you can see, Arabic vectors are good at classifying the green and the pink classes, while the English vector is good at classifying the orange class. So yeah, so now translations are, we now know the translations are really good and are domain-free additional context. Can we just, translate the sentence, run an encoder, for example, CNN, to get features, and then concatenate all the features? The problem is that this does not work well, because again, translation services are still not perfect, and it may just introduce more noise than signals. So in this task, we cannot really classify whether this vector and this vector is positive or negative, or this class or the red class or the blue class. Second naive solution is that why don't we do like regularization, like L2 regularization? The problem is, although this also will weaken the noise, this will also weaken the useful signals that we can use for sentence classification. So in this paper, we proposed multiple context fixing attachment, or MCFA, which has 3 modules, which is the self usability, relative usability, and vector fixing module. So basically, MCFA is used to fix the sentence, the encoded sentence vector into a more correct sentence vector. So from an incorrect vector to a correct vector. So the self-usability module tells us how confident is the sentence feature in solving the task. So for example, we have the movie is terribly amazing. So in this case, it might be hard for the model to classify this or not. So self-usability module is actually the confidence measure of the sentence vector towards the specific classification task. On the other hand, the movie is very good, may have a high self-usability because it's very easy to classify. So in this case, we use a self gate. So we use a self sigmoidal gate here for this self-usability module. For the relative usability module, this signifies how confident is the sentence feature to fix the errors of other sentences. So this is looking at language 1, and if language 1 is helpful in fixing the errors of another language, then the relative usability score will be high. So in this case, we use attention. So we use the sentence to be fixed as the context vector. We calculate an attention score, and then we pool the sentences into one context vector. This context vector will then be used by the vector fixing module, where we try to fix the sentence using again a sigmoidal gate. So again, the vector fixing module signifies how much information should be used to fix the current sentence. So this is the context vector, and then this is the vector to be fixed. We create a fixing vector, which is then feed into a sigmoidal gate, so that we can have so that we would know how much information dimension-wise should be use. So like, because since this is already, so the sigmoidal gate is from 0 to 1. So it's, so like dimension wise, how much information should we use? How much information should we use in this sentence vector to be fixed? So the strengths of MCFA is as follows. So the first one is that it's adaptable to other sentence encoders. In this paper we use CNN, but we can also use RNNs, we can also use BiLSTMs or other kinds of sentence encoders. It's extensible to multiple languages. And we can use as many language and still improve performance instead of like introducing a lot of noises. And then the third one is that we preserve the semantics of the vector dimension, because we just multiply the importance values of the importance values for each dimension of the sentence vector. So for the results, we use MR and CR are sentiment classification task. Sub J is the subjective classification task, and TREC is a question type classification task. And these are the results. So the first result is that we try to compare the translation and the topic as additional context. And here we show that the CNN plus topic context do not work on most tasks, because again these tasks are very domain specific, and since the context is domain dependent, it does not work well. And then we also compared using the baselines that that I showed a while ago, the naive concatenation and the L2 regularization, and we showed that there is a marginal increase from the original CNN base model. And if you use a lot of languages, the performance actually decreases because it introduces also a lot of noises. And for L2 regularization, it also removes the good signals from the original sentence encoder. So MCFA, on the other hand, it provides the largest increase in performance. And when we use 10 languages, the performance actually increases compared to when we use only one additional language, proving the extensibility of MCFA. And we also achieve state-of-the-art on CR and TREC for single models, and MR for an ensemble, for the ensemble of n equals 10 and n equals 1 model. So I actually did not explain what N is. N is like the additional translated sentences that we use for additional context. And so for this experiment, we tried to use the least useful language, the least useful translated sentence, and we show that. And our question was: is MCFA still good at extracting information, even if the language is not really informative? It's not really useful to fix the current to fix English, for example, in this case. And yeah, the answer is yes. But so the baselines did not really work that much, but the MCFA works pretty well, although it's not really the increase is not really that good. But at least it still works. And then here we do analysis on the self-usability. So this just shows that even if we have translation errors, if the translation errors lead to difficulty in classification, then self-usability will be small. But even if there's a translation error, as long as it leads to easier classification, then the score will be high. So for example, in this case, Thirst for Violence is translated into a title of a movie. So this what we interpreted on this example is that since it's already a movie title, it's not really the violent that we know. It's not the violent, the negative violent that we know. That's and this sentence is actually positive, and since violent is negative, this translation actually helps a lot more, even if there is a translation error. So the self-usability score is high. So for the relative usability, So we can ask the question, when is it good or bad to use translations? So here we consider like the useful cases. So relative usability considers only the useful cases, and we can actually interpret the results as follows. We should not use translations if the translation has a lot of error, which is obvious, or when the language is not really good for the task, so such as Arabic or Russian. But we can use translations if the original sentence has ambiguous expressions, such as English, such as this example, or when the language is useful for the task, or when the language is actually better, actually has a good performance for the task. So this is just the visualization of unaltered the fixed and the unfixed vectors. So on the unfixed vectors, it's not actually very easy to separate both positive and negative classes. But here, it actually the separation actually is clear compared to this part. And yeah, so MCFA improves the separation of two classes. So for the conclusion, we have, again, translations. They are better additional context because they are domain-free compared to the previous domain-dependent alternatives. However, we need to fix them to remove the noise from translation errors, and we also need to know which translated sentences are useful to fix the translated sentences that we will use as additional context. And then we propose MCFA with 3 modules for that. And then using MCFA to CNN improves the performance of CNN and achieves SOTA on multiple datasets. So yeah, so this is the end of the second paper. So if there are any questions.
I have 2 questions. So first, okay, so by using some MCFA, right, modules, so how about the increase of parameter size or the training time or inference times?
So there is an increase in parameter size because since we are using different we are using different models for different languages. So there's an increase in parameter size, but the increase in time is not really, because since we are using CNN, we can actually parallelize them. So it's not really big.
Yeah, actually compared to LLM styles models, they are not serious.
So basically, the increase in the parameter size and the time is in this encoding stage, but in this part it's not really. Yeah, it's not.
Okay, second, so here the MCFA had 3 modules, right?
Yep.
So do you have some evaluation studies just using only some usability or relative usability sample and vector fixing, etc.?
We haven't really tried doing ablation tests, but yeah, it's interesting. It would be interesting.
Yeah, so we can check explicitly how to that component side effect on the performance, I think.
Yeah, that's correct. Yeah, thanks.
Thanks.
For the suggestion.
두 가지 질문이 있는데요. 한 가지는 이제 기계학습을 써서 그 기계학습 결과를 피처로 사용한다는 내용 같은데,
네.
기계학습을 썼을 때 예를 들어서 영어로는 아까 뭐라고 했죠? 그 awfully good인가요?
Terribly amazing인가요?
예, awfully terribly amazing이라고 했을 때 저걸 번역했을 때 저희는 이제 끔찍하게 좋다라고는 안 하잖아요. 그러니까 매우 좋다라고 번역이 될 테고,
네.
그런 걸 보면은 그 머신 트랜슬레이션에 의해서 어느 정도 그 센티멘트에 관한 부분도 해결이 됐다고 볼 수가 있을 것 같은데,
네.
그러니까 머신 트랜슬레이션에 실제로는 명시적인이 아니지만 센티멘트 지금 태스크 자체가 어느 정도 해결되는 부분이 있다고 보면 그걸 쓰는 게 뭐랄까 피처 자체가 좀 치팅 같은 느낌이 있지 않나라는 좀 생각이 드는데, 그 부분에 대해서 좀 어떻게 생각하시는지 궁금합니다. 그러니까 MT 자체가 워낙 여러 개를 포함하고 있는 거라서 뭐 좀 그걸 치팅이네요라고 말하기는 되게 힘들 것 같은데,
근데 사실
예.
뭐 트랜스레이션을 쓰는 것 자체가 치팅이라고 볼 수도 있잖아요. 그러니까 새로운 그러니까 additional information을 쓰는 거 자체가 그래서 거기서 이제 나오는 게 또 다른 약간 advantage 같은 것도 쓸 수 있게 되는 게 이제 advantage라고 이제 생각하고 있습니다.
아, 예, 알겠습니다. 그리고 그 머신 트랜슬레이션 결과는 뭐 팝하거나 이런 외부 API를 구글 트랜슬레이션 쓰셨으면 MT 자체에 사실 컴퓨테이션 코스가 엄청 크니까 이걸 위해서 MT를 쓰겠습니다 하는 게 좀 코스트적인 면에서는 닭 잡는데 소 잡는 칼을 쓴 게 아닌가라는 느낌도 드는데 그런 부분에 대한 뭐 리뷰어로부터의 이렇게 공격 같은 건 없었는지 좀 궁금하네요.
일단 그 첫 번째 질문 하신 거에 대해서는 이제 리뷰어에서 이제
예.
그 질문을 했었고요. 근데 그건 약간 어드밴티지라고 생각을 했으니까
예.
그랬고 이제 뭐 예를 들어서 다른 어디셔널 인포메이션을 쓴다고 하면은 예를 들어서 뭐 파일트레이싱을 쓴다든지
예.
아니면 백트랜스레이션을 쓴다든지 아니면 토픽을 이제 LDA에서 이제 추출해서 쓴다든지
예.
다 세 가지 그 어디셔널 인포메이션도 컴퓨테이셔널 코스트가 있거든요. 그래서 예, 약간 뭐 그러니까 이 트랜스레이션을 additional information을 쓰는 거랑 다른 additional information을 쓰는 거 봤을 때, 그러니까 그 두 개를 비교를 했을 때 트랜스레이션을 쓰는 게 더 좋다는 이제 주장을 이제 이 페이퍼에서
예, 알겠습니다. 감사합니다.
네, 감사합니다. Language. So we considered only 10 languages. Yeah. So this part is actually the result where we tried to consider all the 10 languages. So
Yeah, I also want to know that which is the best target language, because once we translate one language to another one, after that we also need like NLP tools to tokenize the language to use that data set into our model. So what do you think the best target language in terms of your experience?
So yeah, we actually did that experiment as well, but we didn't have any space. It's actually different for each task. So for sentiment. So what is interesting is that for sentiment classification, French and I forgot, but like there's this specific language that's better compared to other languages, and then for other types of tasks, then the language another language is better. But there's, I think it was NL Netherlands, I think NL. That language, I think, was like consistently better compared to other languages.
And my last question is, you told that the French is one of the best language, and that the reason is from that the French itself has some different architecture that can be easily adaptable to that.
So we haven't really tried. So we haven't really tried doing analysis or like further analysis, like why is French better compared to other languages? Maybe it's because the linguistic structure is different, or maybe it's the same. But like we haven't really like looked up on those. Yeah.
Then do we have like good NLP toolkit for the French, like tokenizer? The accuracy of tokenizer is also important.
Oh, so that's true. And so we used an off-the-shelf tokenizer. So there's this library in Python called Polyglot, where they support a lot of tokenization tools for more than 100 languages. So we just used that. And again, so I think it's also like the tokenization accuracy is also important. Maybe that's why we also tried to use Korean here, but like the Korean tokenization is actually harder compared to the Western languages. So yeah, maybe that's why Korean didn't really like have a good performance compared to other languages.
Thank you.
I would think that the contextualized work vector would be a more suitable baseline to compare with your method. How do you think about that?
So is it the Cove vector?
Yes.
I think we can also use Cove, but I think it's an unfair it's an unfair comparison towards us because I mean I think because Cove is unsupervised, we are using supervision, like direct supervision from the classification. But like Cove is just using word vectors and then yeah. So like if you or are you saying that we use Cove word vectors?
I want to like just see the like the score boosting.
From just using maybe for example word2vec to Cove.
Yes, exactly.
Yeah. So yeah, I think that's also a good experiment to do.
So if the Cove improves a bit better than your method, then does it mean that there will be like better aggregating method?
Yeah, so I think because Cove is only trained using a single, like from English to French, right?
Mm-hmm.
Or
So I guess like both are in the same spirit in the sense of like distilling the machine translation knowledge to
Yeah.
other tasks,
Yeah.
and the Cove is focusing on the bottom up.
Yep.
You're focusing on the top down.
Yeah, yeah, yeah. So yeah, I think it's really good to like do experiments on both. But I think maybe the disadvantage of Cove is that you need to train a lot. So for example, if you want to use 10 languages, you need to train 10 Coves for 10 languages where
Yes.
you need parallel data. Yeah. So I think I should proceed because I don't have any more time. So the last paper is all about
Hello?
using metadata. Oh, do you have any question?
Yeah, so right now in your model there is no interaction between the languages, right?
Also,
So-
when encoding them, there's no interaction.
Yes,
but like
so-
when you try to fix them, the interaction comes from here. So when you try to fix a certain language, but like when you try to encode them, we just use a separate CNNs
Okay.
for. Yeah. So the last one is an ACL paper on using metadata information as additional information to consider a special case known in sentiment and classification as cold start problem. So again, here the task is sentiment classification, but we are now using review texts as our input text. And in this case, we can get the user and the product information for the review text. So the traditional method is just to use text as features, but new methods are actually using user and product information to as additional information for classifying sentiments. So this is because some expressions have user-specific or product-specific sentiment intensity. So for example, I like salty food, and the food is very salty. For me, it might be that this review text is positive compared to someone who doesn't really like salty food, where the review text would be negative. So the existing solution is focused on like where do we add this information? So how do we add this information into the model? So is it preference matrix to modify word meaning? So like people also try to use memory networks to modify document meaning, attention mechanisms, and so on. And we already have the answer. The answer is that attention mechanism always wins among the other methods. And the current state of the art is using hierarchical LSTM plus the attention with user and product context. So yeah, so in this case they use a hierarchical, so they use a very complicated encoding text encoder and use attention with user and product context. So this is actually the current trend in using user and product information. But so in this paper we argue that the architecture is not really the biggest problem, because the bigger problem is cold start problem, or a problem where useful information cannot be drawn because we don't have enough data. So in this case, so for example, for this user, he or she has a lot of review data, so we can create a representation of this user using these review data. But for a cold start user, for example, if the user just sign up for this review website, so he or she doesn't really have any reviews yet, so we cannot really construct a good representation for this user vector. So this leads to incorrect user and product representations. So our idea is to build a model that is both faster because and more superior by focusing only on the cold start problem. So we will try to not to use a very complicated text encoding problem, but we focus on cold start problem, and the result our results show that we have better results compared to those who focus on the architecture. So this is the model. This looks very complicated, but it's not really complicated. So it has two major parts. The first one is the word encoder, which is called hybrid contextualized word encoder, and the second one is the more important one, which is the cold start aware attention. So for the HCWE, we just use CNNs and RNNs to encode the word and then concatenate them. So it's easier. It's not hierarchical. So it's so much faster compared to the current state of the art. And we extend the current attention pooling mechanism that is used before to support cold start user and product entities. So we call it CSAA, where we have distinct and shared pooled vectors, and then we have a frequency guided selective gate. So the first pooled vector is just the additive attention mechanism. So again, we use user or product as our context vector, and then we do attention mechanism. So this is the distinct pooled vector, and this will be used when the user is not cold start. So if we have a lot of data, we would want to use this as our vector, pooled vector. And then we also have shared pooled vector, where we have, if a user is cold start, then we create a pseudo user vector using other users' information. So in this case, we first do attention over all the over all the users, and then create a pseudo user vector, and use that vector to do another attention mechanism over the words, so that we can create the shared pooled vector. So yeah, so this is just attention and then attention here. And then finally, we use a frequency guided selective gate to select between distinct and shared pooled vector using the user review frequency. So if a user has maybe, for example, 10 reviews, then we use a Weibull distribution to know if 10 reviews is actually if 10 reviews are enough to create a user representation or not. So we use this to control that, and then we use the gate to combine both the shared and the distinct pooled vectors. And then we repeat this for the product vectors, so that we can have the product distinct, the product shared, and the product pooled vector. And then finally, for the sentiment classification, because we have a user vector and we also have a product vector, we combine them using a sigmoidal gate, using this gate, and then we train softmax classifier, because we all know that these vectors are actually on the same vector space, because we just use gates to combine them. So we train a softmax classifier over all the pooled vectors. So we do cross entropy over all the vectors to train our model, and then at test time we just use the final vector to classify the sentiments. So the experiments are as follows. So here we use the original IMDb and Yelp 2013 datasets that are used before, and so simple concatenation of CNN and RNN. So the simple word encoder plus the CSAA is the state-of-the-art performance, and so it outperforms the NSC, which is the state-of-the-art at that time. Then we also perform on sentiment classification on sparse data. So on sparse data, there are more cold start users and products. And in this scenario, NSC actually performs worse than the same NSC without the user product information. So just the hierarchical LSTM. If you just use hierarchical LSTM without the user and product information, it's actually better than the current state of the art at that time. But HCSC, on the other hand, it performs consistently better even when data is sparse. And then again, so this is the time complexity of the models. So we have at least 6 times speed up compared to the NSC model. Here we compare the accuracy per review frequency. So in this experiment, we show that HCSC actually gains accuracy when the review frequency is low. So we compared NSC and HCSC accuracy, and when the review frequency is low or when the user is cold start, we have a big improvement on accuracy compared when we have a lot of data. So in these cases. Then we also look at how we also analyze the Weibull distribution. So the question here is that how few is cold start? How do we use a cutoff point? So for example, if a user has 10 reviews, should we consider that user a cold start user or not? Or for example, if a product only has like 50 reviews, is that product a cold start product or not? So HCSC provides insights through its Weibull distribution. So the answer actually for how few is cold start is that it depends on the context, it depends on your domain, and it depends on whether it's user or product. So the results are users have a more lenient cold start cutoff point than products. So yeah, so these are users. So if, for example, in the IMDb dataset, if we only have 10 reviews, then if the user only has 10 reviews, then he or she is not cold start. And it also depends on the domain of the dataset. So Yelp versus IMDb. And we also tried doing experiments on pooled vectors. So how does this shared how does HCSC create this shared pooled vectors? So first, it creates better representation when user or products are cold start. So this is the example number 1. So the user distinct vector is focusing on the wrong tokens, but the user shared vector is focusing on the correct tokens. And then for the example number 2, since in the example number 2, user and product, the user and the product are not actually cold start. They have a lot of reviews. So what shared pooled vector tries to do is to imitate the distinct pooled vectors when users or products are not cold start. So for the conclusion, so again, we need to solve the cold start problem. So we need to consider the special case on cold start problem if we want to use user and product information. And then we propose HCSC, which has this HCWE word encoder and CSAA attention mechanism. And it performs state-of-the-art performance on both non-sparse and sparse datasets while not sacrificing speed. Questions? No questions. Yeah. So I think I'm running out of time. So I'm just gonna skim through this. So there are issues and possible future work. So for the first one is that we still don't have an exact definition on additional information understanding. This is just a concept that we made in our lab, but again, so there is no exact definition, and in our papers, we just try to fix errors. We just try to solve problems. So, but I don't really think that additional information understanding is equal to just fixing errors or solving problems when you try to apply additional information. So this is an open problem, and I still don't have any answers yet. And I think it will be interesting if there is a theory based on this one. And then there's also an issue on general purpose methods. So in NLP for text, we have general purpose methods such as CNNs to capture phrase level features, RNNs for sequences, etc. Is there a method to understand all kinds of additional information? So again, in our previous papers, we only try to understand a single additional information for each paper, which is not actually a good idea if you want to, because we want to have a general purpose method for additional information. So the answer is, I think no, but maybe yes for those additional information with similar characteristics. So we actually have in our lab in Yonsei University, we have work under submission on categorical metadata representation. So again, categorical metadata, we have user product information from reviews. We also have author venue information from research papers. So since these categorical metadata have similar characteristics, and they have similar and common issues as well, so is there a way to actually create a general purpose method for to effectively represent all kinds of categorical metadata information? So this is ongoing work. We actually already submitted this to a venue, and yeah. So there's also an issue on model agnostic methods. So model agnostic means that the method should be applicable to any kinds of NLP models, because we always have new and better models every year, maybe every month. So before we just use CNNs, RNNs, BioLSTMs, and so on. But like recently we have memory networks, pointer networks, fully attentional models, transformer, and so on. So can we create a model? Can we create models that are model agnostic, or the methods that are model agnostic? And the answer is yes. And we should create only model agnostic methods, because again the field is increasing, and there are a lot of new and better models every year. So again, the methods are actually all model agnostic. So these are the base models that we can change into like a better model. But yeah, so yeah, and then so we also have a question on which task should we focus on? Should we focus on natural language understanding, or should we focus on additional information understanding? And my opinion is that since AIU actually precedes NLU, if you want to understand natural language, we need to understand additional information first, because we would want to use this additional information to actually understand the language. So again, remember the talks of Yejin and Minjun. However, NLU research is also important because it actually has already provided a lot of tools that can also be used for AIU. So there are tools such as like the attention mechanism that we can also use for AIU. And so again, I think both tasks are complementary, and both tasks should be considered important. And then the last issue is on the evaluation method. So for NLP, we have intrinsic and extrinsic evaluations for word or sentence or text representations. So for intrinsic, we can use word or sentence similarity. For extrinsic, we can apply our representation to new tasks and show that that this representation is actually general purpose and somewhat. But the evaluation methods that we use in our papers are only extrinsic. So the question here is that how do we evaluate our models intrinsically? So we need two kinds of data sets. We need natural data sets, which is very difficult to construct. So we need something like a word similarity. But for example, if we want to evaluate our user representation, then we should have human annotations for user to user similarity. So how similar the user is, and that's actually very hard to annotate. We can also use gathered statistics, which is very rarely available. So for example, which languages are useful? So like if there are like research in linguistics that shows that this language is actually useful for to improve English text and so on, or to fix English text, then we can use that to compare to our models. So I would like to end with this Twitter mega thread. This is actually a very famous mega thread on Twitter on semantics and meaning in NLP. So there is this very large discussion between linguistics and computer NLP researchers on how should we represent, how can we represent semantics? How can we represent semantics using a vector? And NLP scientists they argue that we can just use language modeling or translation or RT tasks. So like we can use co-vectors, or we can use the ULM fit vector, or we can use the Elmo to have a very good sentence meaning or sentence semantic representation. But again, Emily Bender, she's very outspoken linguistics. She actually is against that method. So according to her, you can't really learn sentence meaning representations only through forms, only through using language modeling, only through the texts themselves. So we should have something other than the form, other than the text that we have on the language modeling task, in order to actually correctly represent the semantics or the meaning of a single sentence. And again, my opinion here is that how about we try grounding from additional information? And yeah, so that's it. I'm out of time. Thank you.
So apparently you're starting a PhD soon, so are you going to continue this research in this direction, or do you have any other plan? Just wondering.
I'm really excited about this research, but I don't really know what my advisor would want me to do in the future. So I would probably do a part-time research on this in this area too. So
okay, thanks.
Yeah.
Okay, I absolutely agree with you that the additional information is very important to understanding natural language, but actually for real application, additional information to large to something specific, they extract something specific information is one issue. The second issue is some kind of the difference from the representation granularity of natural language style, where the additional information kind of you suggest as kind of some visual information, audio information, etc. This kinds of representation is a little bit different from the natural language intonation. And third is actually for word knowledge is too big to extract some the specific word, the related information from each specific our language information. So it means that there are many research topics. So I think you actually because it's too big issues, so we need some focusing on some as a starting point for the solving tasks. So what is your preferred or the main topics for as your research starting point?
Are you talking about the task, main task?
And the task was some just research topics, etc. for your as a starting point for your research. Yeah.
That's actually a very good question, because I haven't really thought about what research I would like to do. I'm very interested in all kinds of NLP tasks, but yeah, I would really need to focus on one task. So that's a really good advice. Mm-hmm. Yeah. So yeah, I probably would really need to think about it for starting my PhD. Thank you. 감사합니다. Thank you.